In this lesson, we're going to talk about subtraction strategies, and for the purpose of our discussion, I've placed this in a separate lesson. Although in reality, I think you'll see that the work with subtraction is integrally related to the work that you do with addition strategies, and that will become obvious as we proceed. In fact, it's probably obvious immediately from this slide, because as you look at these subtraction strategies, they should look pretty familiar as we think about the addition strategies that we already discussed. We're going to go through each of these and take a look at the facts that are involved and how they might be related to the addition strategies. The identity property relates to the idea that if you add 0 to any particular number, then your sum is equivalent to the original number that you added 0 to. If children have a number bond relationship with this in mind, where they can see a 0 as being one of the parts, then it will be obvious that the subtraction version follows for both sets of these subtraction types of problems, where you're subtracting 0 or where you're subtracting a number from itself. So in this case, after the children have already looked at the identity property in addition, they should, while that's still fresh in their mind, go into the work with subtraction. And that serves a couple of different roles. It solidifies the addition strategy when they have to extend it to subtraction. It also really gets the students thinking about the relationship between addition and subtraction, especially that sort of number bond relationship of the two addends in the whole. That underlying relationship is the same. Even though the addition and subtraction sentences differ in the way we write them in equations, the underlying relationship is the same. So we want children to really focus in on the underlying relationship rather than just getting sidetracked by all the different equation versions. Now, we are going to want them to get good at the equations as well, which is what we've talked about in another lesson. But in the end, we really want them to understand the relationship well in terms of strategic thinking. If they don't understand the relationship, they will struggle. Counting back 1 or 2, if we're only subtracting 1 or subtracting 2, counting back is an efficient strategy. If they have to count back much more than that, they will either be really slow or very error-prone for the most part. And so this is a strategy that we highly encourage when the numbers to be subtracted are small. The Common Core authors have indicated, however, that counting back, while it fits well with a takeaway model of subtraction, isn't necessarily as good as counting up, which fits closer to the missing addend. So many children think of subtraction as a takeaway, and that does serve as a problem down the line. We talked about that in Part A, what kind of problems can occur for children in later elementary if they didn't get that idea of what subtraction really means in early elementary. But we definitely want to foster this idea that subtraction is a missing part problem, a missing addend. And so that's our focus here, and the Common Core authors in this quote talk about the role that counting up can play in reinforcing this idea in children's minds that I'm searching for a missing addend. So in this case, if you are actually, if your subtrahend, that's not a word I would necessarily use with first graders, but if the second number in the subtraction sentence is 1 or 2 less than the whole number or total, then counting up makes a lot of sense. Children should also have firmly established in their minds, by the time you're doing strategy work, the anchor facts. And those would include the sums of 10 for sure, and their doubles facts. So if they understand those, and they understand the relationship between addition and subtraction, they should know all of these facts. The facts that are in an aqua color are technically not within 10, so they're not held to the same fluency expectation. Remember, first graders are to know all addition and subtraction facts within 10 fluently. However, the doubles facts should be known well, so there's no reason why the first graders can't really figure out those subtraction sentences as well. So I've talked several times about this idea that subtraction is the inverse of addition, and while first graders do not have to understand the terminology, the inverse of, that can be a little technical, they should understand the concept of how addition and subtraction are related. And we've talked about this before, the idea that addition is knowing the two parts but not knowing the whole, and that subtraction has the exact same relationship, but in this case it's one of the parts I don't know, and I do know the total. children can use this knowledge if they already have a known fact to construct the missing piece. So in this example, if I don't know 7 minus 3, but I do have in my schema that 3 plus 4 is 7, then if I can understand the relationship between these values, 7 is a whole and 3 is a part, and I'm looking for another part, if I understand that in my mind, I can say, oh, well, the other number you add with 3 to get 7 is 4, so the answer must be 4. Level 3 methods are a little different than what I just described. What I just mentioned was using a relationship, a known relationship in your mind between addition and subtraction, combined with a known fact, something that's already in your schema. Level 3 method involves you doing a little deriving. You don't know that exact fact, but you do know a near fact, and you can use a mathematical relationship to work from what you do know to get to what you don't know. And these methods tend to be based on properties of operations, even if the children aren't consciously thinking about the properties of operations. The strategy itself works because of these properties of addition and subtraction, and children can explore those through the use of these strategies. And it allows them to turn hard problems or unknown problems into easier and known problems. So we're going to take a look at how to do this with some sums of 10 as our anchor facts. But essentially, to use a level 3 strategy, you have to take a known anchor fact, and then from there you have to use it to infer what this near fact is. So consider how that relationship then helps. If I know this, how does that help me solve this problem? Now initially, this is going to be pretty slow. Initially, they're going to have to think, and they may have to study models and try to model it to see why that works. But remember that they are laying a cognitive pathway. Think of it as paving a road. Once the road is paved, they're going to be able to proceed a lot faster on their bike down this path than if it were a rough track. But initially, it's going to take time to build that road. So here, you're building a cognitive pathway as the strategy is being developed. But that is going to pay off in fluency in the long run. And not just fluency, but it's fluency that comes with a lot of number sense, and also base strategies that can be extrapolated with bigger numbers. You'll see that a little bit at the end of this lesson as well. So here's some examples of the remaining facts that we haven't talked about. We've talked about subtracting 1 and 2. We've talked about using the anchor facts. We've talked about counting up if the difference is only 1 or 2. So we do have some leftover subtraction facts within 10, and these are the leftovers. So of the ones that are within 10, these are the remaining ones that we haven't talked about yet. And so here I show you some examples of how a known fact can be used to derive the subtraction fact. And the first few are essentially using a Bevels anchor fact, and the bottom 4 are using a sum of 10 as an anchor fact. So just to give you an example of each, let's take a look at 8 minus 5. That's the third one down. An example could be, well, I know 8 minus 4 is 4, but I'm taking off a little more than 4, so it must be 3. The difficulty with subtraction is sort of figuring out, sometimes kids will say, well, it's going to be either 3 or 5. Although they can think a little further and go, it can't be 5 because 5 and 5 is 10, so that must be 3. But they have to, once they know the anchor fact, they say it's going to be around there. Let me think through how to compensate for what I just did. For using a sum of 10, let's take a look at 9 minus 5. In this case, you can say, well, 5 and 5 make 10, so 5 and 4 must be 9. So in this case, you're using an anchor fact to construct a strategy for how to derive a fact. And that is a possibility in a situation where they don't already have the turnaround fact memorized for addition. Okay? Now we're going to explore the facts we've talked about up to this point have largely been those facts that we have to bring to fluency by the end of first grade, the facts within 10. Now we're going to extend the kind of thing we've been talking about to larger facts that children in first grade are expected to be working with, but which might not yet be at fluency. And those are the facts within 20, and they are on the horizon for fluency. Children will need to have these fluent by the end of second grade, and we expect a number of first graders to be already making considerable progress towards fluency with that set of facts. Second grade is really to ensure that we can extend that expectation to all of the learners, because they, obviously, you've worked with children, you know that they don't all proceed towards fluency at the same rate. Sorry about that. All right, so here we see that even with larger numbers, those same basic strategies that started out with addition and then we use them with the facts within 10, they still work for facts that are larger, and we want children to understand that. Sometimes children will apply a strategy fluently with small numbers, and the minute they say a big number, it's like they don't even recognize the strategy still works here. So we'll want students to really spend time exploring how these are similar to ones they've already done. So the identity property works even with the facts within 20. Countdown works if they're only counting down 1 or 2. Beyond that, it's pretty inefficient. And then counting up if the subtrahend is pretty close in value to the minimum. Anchor facts also work, but in this case we have a new set of anchor facts that we can apply for the facts within 20, and that has to do with the decomposition of the teen numbers. I'm using teen really loosely here to refer to 11 through 19, not just 13 through 19. And these facts were first worked with in kindergarten, so children should have quite a bit of experience. They were supposed to take teen facts and decompose them into tens and ones. Starting in kindergarten, it's also in the Common Core standards for first grade. So this should be one that's familiar to them. I'm going to pause and take a drink here. Sorry about that. Okay, so now we're going to take a look at a level 3 method, and I'm using this one also as an example of a whole instructional sequence, because in order for us to think about this time-wise, we really don't have time to develop every single lesson or every single strategy in an entire instructional sequence for several days. But here I'm going to actually illustrate, I'm going to show you the strategy, and then I'm going to illustrate how that might play out in an instructional sequence. So the strategy is sometimes called the nines trick. I really dislike that term because it isn't a trick. It works on the basis of mathematical relationships, not an arbitrary trick. So I prefer to call it the subtracting 9 pattern. And because I want children to really understand what is happening, I'm going to introduce it with a concrete representation, which you'll see in a minute. But essentially, it illustrates that subtracting 9 is exactly like subtracting 10 and adding 1. So all of these facts where you're subtracting 9 can be restated by subtracting 10 and adding 1. So 20 minus 9, I take the 20, I subtract 10, I add back 1, and that's 10 plus 1 is what it's turned into. 13, if I subtract 10, that gets me to 3, add 1, so my answer is 4. So that's basically the strategy. But just looking at it abstractly here, you see it doesn't appear to make sense necessarily. It does seem sort of trick-like. So let's see how we could explore that concretely so it would make sense. I might use a scenario that you see here where I have a bag of candy and there are 20 candies inside. And I've written 20 minus 9 on the whiteboard prior to actually doing this whole scenario. But I'm not looking at it right now, so I sort of pretend that I don't know that that's what I'm doing. And so I say, okay, I've got 20 candies. I'm going to remove 10 candies from the bag. How many candies are in the bag now? So the children should pretty readily be able to know that there's 10, decomposing 20 into 10 and 10. So then I pretend that I just now noticed that, I was not supposed to do 20 minus 10, I was supposed to do 20 minus 9. So I say, I've got 10 candies here, but I was really only supposed to take out 9. What should I do? I don't think that the average first grader will say, put all of those 10 back and start all over and count from 1 to get out 9. I think they'll typically say, just put 1 back. And so I can put 1 back. And now I can ask them how many there are in the bag. And I think they'll know that it's 11 at this point because they just figured out that it was 10 and I just added 1 back. Now I'm going to act all fascinated with the strategy they've discovered. This is really amazing. I subtracted 10 and I added back 1, and that was the same as subtracting 9? How cool is that? Subtracting 10 and adding 1 is really easy for me, so much easier than subtracting 9. Do you mean I can just use that same strategy to subtract 9 from any number? Let me write this down on the board using the example we just did, and I want to see if it works for other situations too where 9 is subtracted. So we can actually model that. I can then have the students explore using counters and trying the same thing to support that. Then we can come back for a discussion, and during that discussion where they report what they found and we explore to see that it's working, and we can say, well, we want to find out if it works all the time. And so let's explore what's going on, and we can use an equation, a number line. I probably wouldn't use the number line you see here. This one was readily available when I was creating a presentation, but for first graders, we would use a discrete number line or a number path. But basically, you could see that you removed 10, but you added back 1, and that was the same as removing 9. So you can just basically help them see that the reason this works has to do with the proximity of 9 to 10. And what does it really mean, what they're doing when they take away 10 and add back 1. You can also use a visual like this of children who've had some experience with number lines. I find this a very useful representation of the concrete representation, because we can actually keep talking about the bag as we explore this. So I put 20 down and said, that's how many candies I have in the bag. And what's the first thing I did? I removed 10. So then I show that the 20 is being partitioned into 2 10s, and that's the part that's in orange. But then I say, well, what did I do then? Well, you put 1 from that 10 that you removed back in the bag. So then I show that that 10 that I pulled out of the bag was decomposed into a 1 and a 9. And the dashed line here shows that I returned that 1 back to the bag. Now the children can see that we had 10, and then the other 10 is decomposed into a 1 and a 9, and put that 1 back in the bag. Now we can actually relate that to the abstract, symbolic expression, the equations that I have, and think about how this compares. So 20 minus 9 is the same as 20 minus 10 plus 1, and that turned the whole problem into 10 plus 1. Again, we would want to follow that up then with reinforcement activities, where they could get faster with that and get a lot more experience practicing it. So we really want, in our work with strategy with children, for them to recognize that they have to make decisions. Even though here I've sort of classified the different facts into categories where a good strategy would work there, the reality is that often there's more than one strategy that children can use. And so we're giving them a repertoire of strategies through the work that we do on strategy focus. But in reality, we're going to want children to recognize that a lot of the time they have to make choices. It won't always be cued to them, use this strategy, and more than one strategy might work. And that does make for some interesting strategy discussions as well. So we want children to be really thinking about the computation that they're being asked to do, and what facts they already know, what strategies they have at their disposal, what do they know about these numbers and operations that would help them in this situation. So I'm going to go through a couple of examples now where we take the same problem and we see how it can be explored with more than one strategy. So you can see how different learners in your class might choose different strategies, and they might really benefit by hearing how somebody else is doing it, because making sense of both kinds of strategies deepens our understanding of the number system. So this strategy here is called decomposing a number leading to a 10. That's a rather bulky title, so I suggest that a more user-friendly label could be used when you talk with your students. But this strategy is named very specifically in the Common Core, so we're going to take a closer look at it. 10 is a very useful landmark in the number system. Comes in handy for both addition and subtraction. So we're going to use 13 minus 5 as an example. Now the thing that makes this one difficult is that it crosses a decade. So we can reduce the cognitive difficulty by subtracting it into 2 chunks. This is called incrementing, when you do an operation in 2 smaller chunks or more. And we're going to use 10 as a landmark number in the subtraction. Now in this derived fact strategy, the subtrahend, that's the 5, is going to be decomposed and then subtracted in 2 increments with a stopover at 10. So here's an example of a dialogue that might occur as a student shares the strategy. The student might say, well, I took 13 minus 3, that's 10, and I subtracted 2 more, and that's 8. So I might say, you say you first did 13 minus 3, but the problem is 13 minus 5. Where's the 3 you're talking about? Student says, I wrote the 5 into a 3 and a 2, and then I subtracted the 3 first, then I subtracted the 2. So I would maybe afterwards press, oh, I see what you did, and then I would draw maybe this number bar. Class, look at this problem, and I want you to think about why Nina broke the 5 into a 3 and a 2. I'm not breaking it into a 1 and a 4. Turn quickly to your neighbor and tell them why you think she did it this way. So the reason for pulling the class in to speculate on the insight of their peer is that my goal is much bigger than just documenting Nina's strategy. I really want to facilitate the strategic development of the entire class and help them see the power of decision-making in the process of strategy development. So I really need them to be processing the kinds of decisions that are being made in a particular strategy, and I want them to notice the kind of intentionality that Nina used in deciding how to decompose that 5 based on her understanding of the number 13. So it wasn't just what she knows about 5. She also had to be looking over that 13 and saying, if I just could subtract 3, I would end up at 10. So through this dialogue, I want to try to help the whole class become more strategic by supporting their growing awareness of these number relationships. Now, the second strategy is another way that some children might think about decomposing, and this involves working up rather than working back. And the thing that's being decomposed isn't the subtracand. In fact, it's not the 13 and it's not the 5. The thing that's being decomposed is the difference between the two numbers. So we start at the 5 and we add up in 2 chunks. Exactly the same as the top one, only the backwards version of it, right? So I start at 5. First thing I do is add 5 to get to 10, add another 3 to get to 13, and say the difference is 5 and 3 together, joined, because I took those 2 jumps, so it must be 8. So it makes for a really interesting strategy share if you have students doing both of these, and if the children can talk about how the 2 strategies are similar and different, because it contrasts the takeaway model with the missing add-in model, and can strengthen their understanding of subtraction. Here's another example of subtraction within 20 using level 3 methods that involve some decision making. So I have 2 different ways, and you'll notice that I'm showing you some different representations here too. So supposing the children have this problem, Rosa has 17 fish in her aquarium, 8 of them are black mollies and the rest are platies. How many of Rosa's fish are platies? So there's a couple of different equations that could be generated. And notice that 8 plus blank equals 17. There's the missing add-in model, recognizing the subtraction as a missing add-in. Now, that's useful because the problem itself is not taken away. If you read it, you'll notice that no fish are leaving or arriving, none are being bought or sold, and none are dying. So it's actually a missing add-in problem that would be very appropriate for this kind of model. And yet we also know that it is subtraction. So I've shown 2 level 3 methods, both of which involve decomposing a number and using a mathematical relationship and our understanding of subtraction in order to figure out a solution. So in the first example, off to the left, you see that a child decomposes the 8 into a 7 and a 1, and then incrementally subtracts. Again, that's similar to the strategy we just saw, which allows them to have a stopover at the 10. So this allows children to recognize that in subtraction, subtracting 8 is the same as subtracting 7 and then subtracting another 1. So they have to understand subtraction well enough to recognize that. The strategy on the right may be less familiar to you. My younger daughter, who's in Singapore now, tends to use this strategy because it's fairly familiar in that curriculum. It's designed to take advantage of a significant work that's been placed on knowing those sums of 10, which they started way back in kindergarten. In this case, the 17 is composed into a 10 and a leftover, and that's another idea they've been working on since kindergarten. And then they subtract the 8 from 10 because that's something they should be able to do quickly, since the sums of 10 should be anchor facts. So children should just know that when you're taking 8 from 10, you have 2. That should be just solid. And if it is, you can take advantage of it. So I know that if I just took the 8 from the 10, that'd be 2, but I still have the 7 there as well, so that's 9. Because I have 7 plus the 2 remaining from that subtraction. If you have trouble making sense of that approach, try acting it out with snap cubes. Young children aren't introduced to the strategy in the fashion that you see it here. Everything starts concrete. And once children understand why it works, then you build up to this level of abstraction. So I hope you're excited about how to help children become strategic with subtraction by using the properties they've already learned for addition, extending that to subtraction.